here? If I do this, is it better? Worse? Doesn't matter. Here's a banner. Okay. Is that the live stream thing? Yeah. Okay, so you can start the live stream. Yeah. Now that the robustness problem is solved, hopefully, we can get started. Is everything good? Shall we start? Okay. Is it online also? Okay. Okay, let's get started. Let's hope that that won't appear again, but the cost is you're not able to use your microphones right now because apparently there's a robustness issue with the controller. If you try to use the microphones, all of the microphones will go on and it becomes a mess. No one wants that, I guess. That's why we're going to talk a lot about robustness in this lecture. It's a key thing that we need to enable, and clearly we're not there yet. But we need to strive higher, and we need to set the standards to be higher, I think, to enable something like that. Okay, but we're going to get to that soon. So hopefully everyone here is here for computer architecture. Is that correct? Okay. You're not in the wrong room. Pretty steamy here. Warm and fuzzy. Okay, let me get started. There are more people trickling in, so please find a spot. There are spots here. There may be spots in the back over there. I don't know. Pick your spot. Maybe I'll scare enough of you that we'll have a sparser distribution here as opposed to a dense matrix like this. Okay, it's good to be back. I was on sabbatical during the last year or last 12 months at Stanford. So I'm back right now teaching this course again. It's good to have more people, certainly, since this is an area that's going to be a lot more important in the future. Just to give you a brief introduction, I've been here for about 8 years now, maybe over 8 years. Before that, I was at Carnegie Mellon University, a professor over there. And that's where I started teaching this course, actually. Maybe I'll have some stories about that later on. Before that, I was at Microsoft Research. I started the computer architecture group at Microsoft Research, and we did a lot of exciting things, which I may talk about. And over the course of my career, I'm not just an academic in the sense that I actually spent a lot of time in industry also to work with industry, to do technology transfer of some of our ideas into industry, and also push industry to do something more novel than business as usual in general. So I spent time at Google, VMware. That was my previous sabbatical, let's say, Intel, AMD, etc. And some things that are not supposed to be in there also. They're not in there. Consulting, let's say. Okay, so before that, I was in your shoes. I was a student at the University of Texas at Austin. I did my PhD and master's degrees over there. I finished that in 2006. And before that, I was a student at the University of Michigan, undergraduate, and I did degrees over there also. You can find, this is the best way to contact me, my email, and clearly you can find more information about me online. You're here for computer architecture, so we're going to talk a lot about essentially everything that's under this list. I do research, teaching, education, consulting, and all of these topics, actually. But we also do a lot of other things that we're going to touch on a little bit in this course, computing systems, hardware security, and bioinformatics. I'm going to use the first half of this to give an introduction of our group and what kind of things we do and set the mindset a little bit, because I think mindset is really important in what you do, especially in an advanced course like this. But even from the very beginning, it's always good to have a critical mindset that questions things. These things are not talked about in a lot of lectures, but I think it's really important to talk about them and get them straight and in a nice way. Just before I start, how many people? Oh, this is really. I should be standing over here, maybe. How many people here are, let's say, I'll start with masters, since it's a master's level course, master's students here. Okay, great. That's most people. How many people are master's students somewhere else, like some other university? Okay, that's good. We also welcome everyone. We don't say no to anyone. Even if you're not enrolled in this course, you can be here. I have a pretty open view of science and education in general. How many people are bachelor students? Okay, that's a smaller fraction. How many people are bachelor students who took my course? Okay, there's only even a smaller fraction. How many people are PhD students? Okay. How many people are TAs of this course? Okay, there you can see the TAs over there distributed. Some of them don't want to be seen over here. What else? Am I missing something? How many people don't fit in the all of the above categories? Are you sure? So we've actually covered the entire set then with these categories. Okay, that's great. I mean, that the distribution is kind of as I expected, but of course we don't know. Some people may be online. How many people are online? I'm curious. Okay, what about the like Zoom? Okay, so there are some people on Zoom. So you don't have to attend class in person, but I think it's much better to attend class in person. We'll have to solve the steaminess problem of the lecture. Everyone can come in shorts in December, maybe. Good luck with that. Although it's funny. I mean, if you're used to cold weather, shorts don't matter. I used to live in Michigan, and everybody was in shorts in December, January. They wouldn't care. Okay, anyway, let's not digress. So this is my research group. This is an older picture. You can learn more about them online. I'm going to breeze through some of these slides. I'm going to introduce some of these folks tomorrow, actually. These are some of the other like newer versions. We release newsletters. So if you want to learn about the research we do, you can read these newsletters. You can learn more about people, etc. And if you want to learn more about research, clearly we're going to cover some of the research that we do in this course, and also some of the research that's happening in the field, not just what we do. But if you want to learn more about what we do, we have videos that explain it more. And these are people who are our alumni, at least the PhD and postdoc. We also have a long list of masters and bachelors, etc. And you can learn more about them online as well. Okay, if you want to learn more about some views that we have on computing features, I'm going to provide you enough views over here, but you can have more online. And we have a lot of material online that provides suggestions on research, education, and PhD. Okay, let me cover a little bit of what we do today. So basically, clearly you're here for computer architecture. We do a lot of computer architecture, and today is an exciting time to do that. But our really goal is to, our long-term, as well as short-term goal is to enable fundamentally better computers. So to be able to do that, you need to re-examine the entire stack, I think. We look at processor design. We look at different types of processors. Some of these are accelerators. Some of these are graphics processing units. And we look a lot into memories. In fact, in this course, I'm going to start a lot with memories because that's one of the major bottlenecks. I would say memory and interconnect, both of them. There's an interesting interplay over there. And also, we do a lot of work on storage, memory interconnect with processing capabilities. So I'm very interested in new paradigms for computation, some of which we're going to talk about, but some of which may not be, we may not have enough time in this course. These are some of the major current research topics that we're going to touch on. You've already seen the importance of robustness a little bit, I think. Robustness is really, it encompasses security, reliability, safety, availability. So we work on fundamentally robust architectures. We're going to talk about them. I'm very interested in designing fundamentally energy efficient architectures. Today, we actually have architectures that waste a lot of energy. We're going to discuss that. And this leads us to more memory-centric or data-centric architectures. We're going to talk a lot about that in this course. I'm very interested in reducing latency in general and making things predictable, meeting deadlines, for example. I think we're going to talk about that in the course. And I'm also quite interested in fundamentally intelligent architectures that can actually improve themselves over time, as opposed to doing the same thing they were doing 10 years ago. If you're doing the same thing that you were doing 10 years ago, you're probably not progressing, right? Of course, you could be doing worse things. that's a worse situation. And I think in general, I believe in making better progress. So it's good to strive for systems that can do better over time, and using machine learning or AI to actually assist the decision-making process in hardware or software, so that systems become better over time, is really an important direction, in my opinion. We're going to talk about that also. We have some research in that area. And then there's also designing architectures, specializing architectures for important workloads like machine learning, genomics, medical workloads, health, space, space meaning outside world, is very interesting as well. And we may touch into some of these. Actually, we're going to touch into some of these. By the way, feel free to ask questions. I have a lot of slides. These slides are actually to be covered today and tomorrow, plus the course logistics tomorrow. And you have the slides online, so they're all online right now. You can follow them as well. We're going to see the slide multiple times. In fact, if you've taken the digital design and computer architecture course, you may have seen it. Well, you must have seen it because I cover it. I cover actually each portion of it. So this is the transformation hierarchy we built today. We have problems to solve, and in dominant technologies today, we have electrons that are orchestrated in the end to solve those problems. Clearly, humans have not figured out how to speak the electron language yet. So we have to translate the problem to an algorithm and translate that to some other language that we can really program in, and then translate that to some machine language that the machine can understand, and then translate that to execution in underlying logic circuits, microarchitecture, and then translate that to the operational principles of the devices, and which in turn really operate based on the principles of physics, which is electrons in the end, right? So that's why we have built this transformation hierarchy. And I didn't talk about everything over here, but if you want to have a stronger treatment of this, definitely look at the digital design and computer architecture course, which is the required freshman course here for the computer science program. It's a rigorous introduction to computer architecture. How many people have taken a course like that? It's a dangerous question. Okay. How many people have taken that course itself? Digital design and computer architecture. Like when I taught it, or when, okay, so there's a small fraction. Interesting. Maybe everybody else is, because we have a lot of people registered for this course, and maybe some of them say, oh, okay, the first lecture is going to be what I know, and they're not here. But there's always new insight you can gain, potentially. Okay, so computer architecture has traditionally been about the hardware and software interface and the microarchitecture levels. Hardware-software interface is what's visible to the programmer and the higher level compiler, software, etc. Microarchitecture is the underlying implementation of that interface, essentially. But in this course, and in essentially all my courses, we take a much broader view of computer architecture, which really expands from algorithms to devices. We still keep this interface and microarchitecture at the center. But today, if you really want to build efficient, high-performance, robust, secure systems, you really want to optimize across the stack. And I'm going to show you some examples of that today. Basically, I already said this. Today, we really need to co-design across the hierarchy, change the devices so that they fit the algorithms, or change the algorithms so that they fit the devices, or co-optimize both at the same time so that you get a better system solution. Of course, this makes it much harder, right? Now you're kind of breaking the abstraction layers that are much more easily programmable and set, but this can give you much higher efficiency and performance and robustness, etc. And this is already happening, actually. I'm going to show you some examples after I introduce the group, etc. And we want to specialize as much as possible within the design goals today. So our research is actually across the stack. We do broad research spanning applications, systems, software, logic, circuits, with architecture really at the core of it. Okay, let me give you some principles that I like thinking about so that I can set the mindset of the course. And it's important to do this in the first lecture so that you can see what's coming next in that way. I care a lot about teaching. I think teaching and research are really two sides of the same coin, right? Research is about, so teaching is, it's not easy. I'm not going to call it easy. It was a nice break during my sabbatical not to teach, frankly. Sometimes it's good to have a nice break because teaching all the time if you take a step back, you can actually see things a little bit differently. And I actually think I see things a little bit differently right now. But teaching is really providing education to other people about things that everybody can figure it out, right? It's known thing. It's a known concept, right? Whereas research is educating others about things that no one knows about. That's the major difference. Basically, you figured out something new and educate someone else. So education is really part of research itself as well. That's why researchers, when they actually find something new, they don't go to a corner and sit by themselves and say, oh, I found something new. This is great, right? What do? They write papers. They go to conferences. They explain it to other people, right? That's how you spread the knowledge. And that's how new teaching material comes about, right? So the teaching material that we're going to cover today was research material some number of years ago. Some of them 80 years ago, some of them 40 years ago, some of them a few months ago. So we're going to actually cover a lot of research also in this course. I like this analogy of researchers sitting around, because some researchers actually do that. They figure out something and they don't tell anyone about it. And in the end, somebody will know. Companies actually do that, right? They want to keep it to themselves for other reasons. You can take issues with that, etc. But that's how it is. Okay, so we do a lot of open sourcing. So just to give you an idea, we have other courses also. This is online. This is an older version of this. I give the digital design and computer architecture lectures. You're here for the more advanced computer architecture course. We don't call it advanced in the, I think, in the course curriculum, but it's really more advanced compared to the first one. And even though there's some overlap between the two, there's a huge disjoint part, as you will see if you've taken both. So if you take this course and if you're really excited about computer architecture, I would suggest still looking at the first course, because there are things that we don't cover. For example, we're not going to touch a lot about processor microarchitecture in this course. Whereas the first course, digital design and computer architecture, is all about how do you design a high-performance processor microarchitecture, out-of-order execution, load store handling, internal GPU architecture, etc. Although we may have some lectures on GPUs because they actually are really important in some of the things that we're going to discuss. And then we also have a seminar course where we cover papers. So if you're interested in paper reading, critical analysis, etc., I would suggest taking the seminar course. This is a much smaller course, of course. And we ask the students to present a paper, and then people discuss that paper. Okay, all of our courses are online. And these are some more links. I'm going to go through these relatively quickly. You can find all of these on your slide. This is for people who may be interested to look at these later. You don't have to in the end. But if you think you're missing, for example, some background in some topic that I cover, feel free to take a look at these materials. Feel free to ask us about what to look at also. But you can find these easily. It's beautiful today, but because you can find essentially everything online. But these are something that I can watch for. I cannot watch for everything online, clearly. Okay, so these are courses. I'm going to go through these relatively quickly. We also have some more specialized courses. We're going to talk about some of the issues that are in these courses. But if you want to go into more depth, you can look at these courses or take them if you're interested, or just study them. There's a processing in memory course. We're going to talk about processing in memory a lot in the first few lectures. And genomics course and heterogeneous systems course, which talks a lot about GPUs. If you want to learn about GPUs, GPU programming, heterogeneous systems, take that course. Hardware, software, co-design. Some of these are also taught this semester and later semesters. There's an SSD course, and there's a list of hands-on projects and seminar courses that change every semester. So this was last semester. I don't have it this semester yet. Although it's online, I just didn't copy it yet. Okay. We also organize a lot of special sessions. Essentially, we put everything as much as possible online, unless we're bound by some other agreement that we cannot put online, which doesn't happen in general, but it could. So if you're interested in learning more, I'm going to point you to a lot of different resources, but you can also find a lot of resources online. We have been organizing processing in memory tutorials, which I'm going to talk about in major conferences. And again, all of these links are online. In fact, we have attendance online also. Probably we have people attending this course online as well, right? Okay, there's an upcoming PIM tutorial that Geraldo will deliver at Micro this year. So I should also, now that I picked on Geraldo, I should say that there's a set of teaching assistants in this course. They're all my PhD students or interns who are doing, or master's students who are doing research. I would suggest you get to learn, know them. And if you're interested in doing research, for example, you can talk to them about their research. Geraldo is graduating soon, so this is a good time to pick Geraldo's brains. He probably will, well, he hopefully will not be here in the next incarnation of this course. Yeah. Okay. Well, I don't know. This is out of order. So clearly there's out of order things here. Okay, we do a lot of open source artifacts. I think I want to say this because this is also important. This is part of the philosophy and mindset we have. This is kind of unconventional in computer architecture. People used to not put a lot of stuff open in computer architecture. Even putting papers online on archive was frowned upon at times, but we basically said we should disseminate knowledge. So that's why everything is open source, everything as much as possible again. So you can find a lot of these. In fact, you're going to do some exercises with some of these open source tools like Ramulator. No, is that true? Or do we have Ramulator 2 in that assignment now? Familiar too. Okay, that's good. And some upmem, which is not already here, like prim benchmarks. Actually, it's here. Yeah. Okay, cool. And you can find a lot of information on my website or linked from my website here. Okay, let me go through any questions so far. This is basic material, hopefully not too technical yet, but we're going to get very technical soon. But before I do that, I want to cover some basic principles we follow. I don't want to bore you with this thing, but some of these things are really not talked about in lectures, I think. And I think it's really important to set the standards. Maybe there should be actually courses in the university very early on to set mindset, because sometimes people get into mindset that's not necessarily academic, in my opinion. So I already said this. I think teaching and research are both very important, and we treat both of them as of equal importance. I care a lot about insight. In the end, developing new insight is really, new ideas is really what enables progress, right? That's what research is, enabling new insight. And this comes through new analyses, new ideas, etc. So I'm very encouraging. So if you have new ideas about how to design a computer architecture, please talk to me. And you have kind of easy access to me over here because we're physically close by located, right? I like focusing on learning and scholarship because in the end, these are the things that really matter, right? I mean, focus could be on money also, right? That's not our focus here. We're not a company. Our goal is not to make money over here. Our goal is to really advance learning and scholarship. And those are the real big principles and pillars we build on. For this, I think it's really important to have an environment that values free exploration, a lot of freedom in exploring new things, openness, open exchange, open collaboration, open ideas. Creativity is important. And I think in the end, hard work is really important also, because it's very hard to get somewhere without doing the hard work. Because if that were possible, anybody in the world could do it, right? It's similar to what I tell people about getting a PhD, right? Do you really want a PhD? Well, think about it. Not everybody in the world gets a PhD in the end. If you have to really want something like that, and you have to really, let's say, have the fire in your belly to achieve something big, right? Okay. So in the end, I think the quality of your work defines your impact. So this is part of the learning and scholarship, and I strongly believe this. Your work may not be accepted initially, but if it's really high quality and if it really addresses an important problem, and if it's really solving a problem that's going to be important in the future, for example, it will have impact. You just need to believe in it. This doesn't mean that everybody else in the world will believe in it right away, right? In fact, it's been shown many, many times that people who are at the edge of the field figure out something, and people who are also edge of the field may not believe them, right? I can give you examples of that later on. Okay, so my suggestions to you in approaching this course, and maybe a lot of other things as well, is to follow your passion. Don't get derailed by these naysayers who may not believe in things. Of course, be reasonable in the sense that take their feedback and see if it makes sense or not, or are they really approaching things in a very biased way, or in a worldview that's really tightly integrated with how the world has been, as opposed to how the world should be, right? We're going to talk a lot about that with the, for example, processing in memory and processor-centric paradigm versus more memory-centric execution paradigms. So clearly there's a huge mismatch over here, and people who are very much used to doing a computation in a processor-centric way cannot even think about putting the computation somewhere else, in memory, for example, or in storage. So it's important to keep this in mind. I'm going to give you examples also in later lectures about some of the comments that we have received in some of these works. So hopefully that'll be educational. How many people here are like pursuing research? No one, other than the TAs, of course. I know TAs are pursuing research. No one? How many people are interested in pursuing research at some point? Okay, that's even more. That's great. Yeah, cool. Hopefully there will be even more hands in the 5th lecture or 10th lecture at the end of the class. Okay, building infrastructure is important, but I think a lot of these actually apply not to research as well, I should say. If you want to, let's say, change the world, if you want to do something different and also make money at the same time, then you need to pursue some other route. And in that other route, things are not going to be rosy. People will not say, oh, come, we'll give you all the money you want, and we accept all of what you do, right? There are a lot of startups, and most of the startups die without making money. you have to really follow your passion and figure out how you actually sell your product, especially if you're doing something very different. We're going to talk about some of those actually in this lecture a little bit too. Okay, building infrastructure is necessary, I think, to enable things like this. You cannot escape from this, and I'm going to show you examples of how we have built infrastructure. And this is the nitty-gritty, basically. Basically, a lot of things that you do in doing something big is really spending time on doing small things. And there are many such small things. Like there's a saying, you basically spend 99% sweat for 1% pearl. Probably it's more 99.9% sweat for 0.1% pearl. But in the end, you get the pearl. And the expected utility of the time you spent for that pearl is much higher, right? How many people know about Pascal's wager? Nobody? Yeah, you know about Pascal's wager. You studied in philosophy? Okay, great, yeah. So Pascal makes a similar argument about believing in God, for example, right? I'm not taking any sides over here, but he suggests that the expected utility, with a lot of assumptions, of believing in God is much higher than not believing. Because even though the probability may be extremely low that he exists, the reward that you would get if you believed in him, assuming all of those other assumptions are true, is going to be extremely high, right? So research is kind of similar. I don't know how I came up with Pascal's wager, but it's good to connect the fields, as you can see. Right? Okay, so work hard, basically. Okay, I think resilience is important. In the end, I think a lot of things boil down to making things happen, right? You have an idea. The idea is out there. Nobody believes in it. You're supposed to make it happen. And if you make it happen, then you succeed. Even if you make it mostly happen, that's also good, right? But this requires a lot of resilience and focus in the end. Okay, and I think I go back to learning and scholarship over here. I already said some of these. So I believe actually every one of you can make a good impact on the world if you follow some good principles and have a good mindset and set your goals and focus accordingly. And I hope that this course will help you do that. Okay, I have some of these covered also in some other talks. So if you want more of this philosophizing, you can find online. I think I have some other examples over here than Pascal. More on quantum physics over here, but I'm not going to talk about that right now. Okay, there's some required reading, which kind of is along the same lines. This is not from me, thank God. It's from Dick Hamming, because he actually did a lot of really interesting work, which I'm going to reference also today a little bit. How many people know about Dick Hamming or Richard Hamming? Okay, that's good. What do you know him for? Hamming distance, excellent. What else? Hamming distance actually, yeah. Hamming codes, error correcting codes that are built on Hamming distance, exactly, yeah. That's part of what he done. He spent a lot of his career in AT&T or Bell Labs before they became AT&T. And this is a talk he delivered. I'm going to actually reference this in a little bit. So how to approach this course? I think this course actually follows a lot of these principles, I think, some of which are outlined in this required reading, in my opinion. But it's not an easy course. So if you are here to get an easy grade, probably I'm not going to promise that to you. Well, remove the probably over there. I'm not going to promise that to you. But hopefully this could be a formative experience. These are actually comments from some people who have taken this course in the past. So hopefully it will enable you to think about some things that you don't normally think about and maybe apply them in the future, right? High investment, high return. You can see some of the comments. These are not my comments. These are students' comments. Recorded lectures allow me to go over. Actually, right now it's live stream lectures plus recording, etc. So I hope that's useful. I don't really care how you learn, frankly. Everybody has a different learning method. In universities and in regular education systems, I think we kind of don't understand that everybody has different learning methods. We kind of try to shoehorn a single method of learning to everybody in the world. At least in this course, we try to be a little bit more flexible, maybe not overhauling the entire system, but you don't have to come to the lectures, for example. Of course, there are some things that you can benefit if you come to the lectures, like you can interact, you can ask questions, etc. You can have a different environment, but you can also follow this on your TV, drinking beer, doesn't matter, or your favorite thing, or smoking pot, whatever. Yeah, right? Yeah, up to you, basically. If that enables you to learn better, That's fine, right? Okay. Yeah, and I'm actually, I wanted to highlight this because I think I would like to encourage participation. If you have questions, if you have comments, if you have ideas, you can feel free to inject them during the lecture, after the lecture, online, whatever, basically. But if you have a question, for example, if you have a burning question on something that I presented, please feel free to ask. Don't keep it to yourself. If you have that question, probably someone else also has that question, right? And maybe that's useful for many other people. So don't be shy. Okay, yeah, I'm going to skip this one, but you can read. Yeah, I'm going to talk about course logistics later, but we have a very simple format where we have homework, labs, and lectures. Well, there's an exam also. I guess they forgot the exam over here. They didn't want to think about it at the time, maybe. But there's an exam, but it's not it's a small fraction of your grade in the end. In the end, my goal is not to really. In the end, this course is actually not that hard to get a good grade on. You need to do more work, but getting a good grade on is relatively easy if you actually do the work, because there are a lot of extra credit assignments, etc. And we're not very exam focused. Since it's an advanced course, we reduced the exam to about 30%, I think, if that's correct. And that's not a big fraction of the grade. So if you get 0 on the exam, you can still pass the course, basically. In fact, you can almost still get a pretty high grade if that's what you care about. I don't think that's what you should care about, but if that's what you care about, you can still get a pretty high grade. Okay, yeah, as you can see, we'll have paper reviews, assignments, and labs also. Labs are important. That gets you the hands-on experience to build different parts of the system. And we have actually 6 different labs. We're thinking about adding 1 more as a bonus. Let's see if that happens. Okay. Okay. I hope you will end up writing this in the end. I don't expect everyone will write this, by the way, but I hope that at least some of you will get to that point. Okay, so I think the best way to approach this course is a learning experience. Hopefully not for grades, right? Grades are, in the end, if you, 20 years down the road, nobody's going to ask you about your grades, right? Especially at a master's degree, and definitely not at a PhD degree. If you're doing a PhD, nobody cares about your grades. Everybody cares about what have you done. Okay, so hopefully the learning experience will enable you to do things that you can tell other people and you can be proud of. And I think one of the things that I would like to enable you to do is to do trade-off analysis, because computer architecture and computer engineering in general is all about trade-offs and analyzing them in an impartial, objective, scientific manner. And this trade-off analysis can hopefully enable you to do many, many other things. So there are people who have taken jobs after taking my course in business, etc. And this trade-off analysis is everywhere in business as well, right? So it's much bigger, essentially. And critical thinking and decision-making based on that trade-off analysis, or enabling that trade-off analysis, is really important also, because if you want to do a trade-off analysis, you really need to think critically about what you're examining. Right? We're going to talk about, for example, processor-centric systems. If you want to look at the trade-off of that high-level paradigm, you need to think critically. Okay, so we're going to focus a lot on concepts and ideas. So in a sense, this course will be quite theoretical, but although a really pure theory person would be very annoyed at what I just said, because it's not really theory. It's not theory in the math type of theory, but it's theoretical in the sense that it examines ideas more or less theoretically. Right? We're not going to basically look at every single evaluation of an idea. We're going to look at it at a higher level. These are the trade-offs, strengths and weaknesses, etc. We're going to focus a lot on fundamentals as well as cutting edge. So that's going to be important. And we'll have a hands-on learning component, which is the labs, essentially. And some of the homeworks will actually have you do some hands-on, programming, etc. Okay, in the end, I believe this is not just true of this course, but this is true of everything that you approach in life. Your mindset will determine what you get out of that thing that you approach. In this particular case, it's the course. So hopefully you have a good mindset, and hopefully I've contributed a little bit to revise that a little bit if it's not in the right place. Any questions? Or even if it's in the right place, hopefully I have reinforced it. Okay, so a little bit more about, given that we've ended with mindset, I think this nice transcript of Richard Hamming's exit talk at Bell Labs is a good example. There's a video of it also. I don't think I like the video as much, but you can really read this. And this is a required reading, and we ask you to do a review. I think it's part of homework 1, right? Okay, homework 1, which will be released at some point in the future. We're going to talk about course logistics tomorrow. So if you're, I'd like to read this actually, because this is one of the paragraph, or 2 of the paragraphs. And this is the camming, by the way, with this cat. You can compare that to your own cats if you have cats. Okay, so this Hamming says, if you really want to be a first-class scientist, you need to know yourself, your weaknesses and your strengths, and your bad faults, etc. And he also criticized himself, as you can see, which is good. It's always good. But basically, I think this is not just about being a first-class scientist, but if you really want to improve yourself, you need to do all of these. And assuming you're a scientist, you should really improve the world, right? How can you convert a fault to an asset? How can you convert a situation where you haven't got enough manpower to move into a direction when that's exactly what you need to do? Okay. And then he basically, I think, summarized a lot of examples in this transcript and says a successful scientist changed the viewpoint, and what was a defect became an asset. And that's actually a very good way of thinking about things, right? Not everything is a defect. And defect, in one perspective, a defect may really be a defect if it's not used in the proper way, right? A defect may actually become an asset. Right? It's good to think about that. And he has some examples, so I'll let you read the transcript. So, okay, I think it's also interesting. This is, of course, his personal opinion. I agree with some of these, actually. I claim that some of the reasons why so many people have greatness within their grasp don't succeed are they don't work on important problems. They do not become emotionally involved, meaning they really push hard, right? Focus. They don't try and change what is difficult to some other situation, which is easily done, but is still important. This may be hard to read, but you can think about that, etc. They keep saying that it's a matter of luck, but it's not really a matter of luck, essentially. Right? So in the end, luck is part of it. In fact, how many people know about Louis Pasteur? Probably more people than, yeah, somewhat, yeah. One of his famous quotes was, now I'm blanking right now, but yeah. Basically, chance favors the prepared mind, right? That's okay. Now it came back to me. It was getting fetched from the storage hierarchy all the way. Maybe I'm processor-centric, as you can see. I hope not, but there's some other association that didn't happen over here. I searched for Louis Pasteur and nothing came about for a while, but in the end it came. I hope it still comes 40 years after this, but that's another issue, right? That's something we're not going to solve in this course. But basically, chance favors the prepared mind, right? Luck, you may say, oh, this person got lucky, but maybe there's something else going on over there, right? Maybe there's a part of luck, but maybe they actually biased the coin a little bit so that they actually seemed lucky, right? So if you are actually prepared, you're much more likely to see the opportunities. So if you don't know a lot about, for example, a topic, it's very unlikely that you're going to get lucky to do some big contribution in it. If you actually know a lot about some topic, you can actually, and also you can think critically, you can actually become lucky much more easily than someone else could. Okay. Okay, now I think we've come to the next part of the lecture. Any questions on these topics? We need to solve this bright shining light problem. I think I have a solution, but I don't want to move this yet. I'm going to move it in the middle of the lecture. Which also you should remind me. So we are here from 1:15 to 4 p.m. Which means that we could take 2 breaks or we could take 1 break. What do you think? I guess we could take 1 break at 2 or 2:15. Let's see. Okay. Unless you're already exhausted. I've already hammered you enough. Not yet. Okay. Okay, so let's now jump into a little bit computer architecture. Again, I want to give you a broad overview of the field. Clearly, I cannot touch on everything, but today is a very exciting time to do computer architecture. If you're taking DDCA, some of these slides are going to be similar, but we're going to diverge soon. Essentially, I think of computer architecture as enabling better computing platforms. And in the end, we have to answer the question, right? Why do we actually care? Why do we even do computing? Does anybody have a good answer? Okay, yeah, that's actually close enough. Solve problems, basically. I would say more general, solve problems, but that's good. And then the question is, well, we can reword this actually. Hamming, this is the same person with his cat that you saw earlier, said that computing is all about gaining insight. It's not about crunching numbers. And he was actually doing a lot of things at a time when everybody was excited about computing because it was about number crunching, right? He said, in the end, we don't care about any of those numbers. Those numbers should lead to insight, right? And that's the real purpose of computing. Today, we have a lot of number crunching going on also, especially with machine learning workloads. Are they leading to good insight? I don't know. We'll see. Hopefully they will, but that's going to be important to think about. And if you extend this answer, hopefully to enable a better life and future for everyone. So then the question is, how does a computer solve problems? We've kind of covered this by orchestrating electrons in today's dominant technologies. Maybe there are some other technologies where this may not be the case, right? You may be orchestrating biological cells, for example, to do computation. You may be orchestrating something else. But in the end, those are also consisting of electrons, but not just electrons in the end. Okay, so how does the problem get solved by electrons? Then we build the transformation hierarchy that I already mentioned, which I'm not going to go through again. And the narrow view of computer architecture has been this. So we're going to take a much broader view of architecture, which I think is already happening in industry, but we should also see that it's happening in industry. So whatever you see in this course, I think is actually going to be immediately useful when you go out, because everybody is doing this right now, which is the good part. When we were arguing people should do this, not many people were doing it at the time, but now I think everybody has realized the importance of it. Okay, so just to define things a little bit more clearly, computer architecture is a science and art of designing computing platforms. And again, I'm going to give you a broad definition over here. It's really about designing the hardware, interface, system software, and programming model, and maybe beyond that also. And the goal is really to achieve a set of design goals. And these design goals are dictated by what you're designing the system for. It could be, for example, a supercomputer. I want to get the highest workload, highest performance on Earth on some 3 workloads, X, Y, Z, or 1 workload. Right? It could be the LLM of your choice, or the whatever. There are lots of LLMs today, right? And this is actually happening today, as you can see, right? It's not, but of course, you should always think critically. Is this what should be happening? That's always a good question to ask. Or should it be happening the way it's happening? That's also a good question to ask. Okay, another goal is to have the longest battery life at a form factor that can fit in your pockets within some cost budget, right? This is like a cell phone, for example, or smartphone, or mobile computing. Another example is more general purpose computing. I want to get the best average performance across all known workloads, or all workloads that I care about, which is greater than 3, usually maybe 1,000, 10,000, who knows. At best performance cost ratio. That's more general purpose computing. So in the end, there could be many design goals, and there are many metrics that you evaluate the system with. We're going to talk about metrics later on. But and designing a supercomputer is clearly different from designing a smartphone, but many fundamental principles are really similar in the end. You have computation, communication, and memory, and you provision them in different ways, and you connect them in different ways in the end. And of course, then there's the execution model and the principles of execution that you should think about also. So we're going to talk about a lot of those in this lecture. Just to jog your creative juices, maybe, I'm going to show you some pictures. These are computers that we have in our lives. And you can imagine others that are not in these pictures, maybe. This is Mr. Bean's computer. I like this one. He envisioned self-driving cars in a maybe more reliable way than we are doing right now. Yes, he has a lever over there that he keeps driving the car with. This is another self-driving car. These are nanopore sequencing engines, so genome sequencing. That's an area we work on. I'm going to talk about that more in some of these lectures. This is a system in your pocket. It's actually pretty powerful, very powerful. This is a data center, which kind of looks like a supercomputer, but they're designed for very different purposes, right? This is another supercomputer. I could keep going with all of these pictures, but copying and pasting from the internet is not the task I like. But some of these are nice, of course, right? This is a systolic array. How many people know about systolic arrays? Okay, some people. That's good. So if you took DDCA, you would know about systolic arrays. Now you can learn about systolic arrays. But basically, this is a specialized architecture to do matrix multiplication. And the goal is to really accelerate machine learning, inference, and training, the core of which is really matrix multiplication. And systolic array happens to be a nicely specialized architecture to do this very, very efficiently, so that you don't need to move the data a lot, at least too much, let's say, between the memory and processing units. The idea of systolic arrays was proposed in 1970s by H.T. Kung, who was actually a professor at CMU at the time, and he actually built some of these systolic arrays also, but no one really picked them up until machine learning workloads became one of the most important workloads, and everybody's designing systolic arrays right now. Google is not the only one. And this is one of the early systolic arrays. Okay, basically, the basic idea is very simple. You orchestrate the input data such that input data flows through processing elements that are not shown over here. And as data flows, the processing elements work on the data and do the matrix multiplication, right? Entire matrix multiplication, and comes out somewhere, either present in the array or outside. So there are multiple ways of doing it. Okay, there are newer versions of this. As you can see, these are complicated systems. So systems companies like Google are designing their own chips, as you can see, because this is an important workload. They do a lot of machine learning inference and training. And they basically said, this is much more cost effective from our perspective to design our own hardware and the software stack that goes on top of it, so that we can actually do this much more efficiently in-house without buying somebody else's hardware. And they have built the entire hardware and the software stack for it. This is not the latest generation. I think there's a TPU v6, for example. But these are pretty complicated systems. They do training, etc. I think they have high bandwidth memory. I don't know if they have high bandwidth memory over here, but anyway, you'll find it. This is another accelerator, another company that presumably does self-driving cars, is actually doing their own chips, as you can see. I think they call this the self-driving chips. And for better safety, they have 2 redundant chips. So they exploit principles that we will cover in this course, dual module redundancy. But they also design systems for machine learning training. I believe they also use it for inference. Essentially, this is another architecture where they can do a very efficient matrix multiplication. And they build a system on top of this. So they design that to actually multiple chips, both interface chips as well as training chips, etc. But you can learn more about it. I'm not going to go over one particular company's products over here. But I should say that the reason they're designing it is, again, they have a lot of data, and they need to train these models that they need to use in their cars so that they can make decisions as to how to self-drive, right? So by collecting data, they can train a very large machine learning model that's hopefully accurate. If you're driving a Tesla, at least in self-driving mode, you should hope that it's accurate. That's the best you can do because there are no guarantees. It's worse than the microphone problem we're having, I think, over here, because your life is at stake or somebody else's life is at stake there. But basically, to go back to the topic, they figured out that it's much more important for them to develop their own hardware such that they can customize the hardware to the software stack they have, and they can adapt the software stack to the hardware they have, and they can co-optimize across the stack so that they can do this much more efficiently, both in terms of performance as well as total cost of ownership. That's what they claim, at least, right? And it's good, I think, that companies like this are actually designing their own systems internally. So this is actually, in a sense, like I was studying computer architecture in 1990s when general purpose computing using CPUs was the dominant paradigm, right? That's the thing to do, and everything else is fringe. GPUs were fringe at the time. Today, everybody is designing specialized systems that look like this, as you can see. And I like this picture over here because it's not just about the chip. It's really about designing the system on top of this. And on top of that, designing the software, including compilers, operating systems, etc. Okay, this is another picture. This is a GPU. These were at the fringe in 1990s and a good chunk of 2000s, I would say. But now they're the king, if you will. NVIDIA was a very small company trying to compete with Intel at some point. But now they've taken over Intel for various reasons. But you can see that this is actually growing. I should also point out that it's not just about the chip. The chip is growing, as you can see. There are 200 billion transistors in the recent incarnation of a GPU. This is massive parallelism in a chip, and we're going to cover maybe some of the principles. But also, I should say that connecting these GPUs to each other becomes very important if you want to scale up the system. And that's why these folks invest a lot in interconnect technology, which we're also going to cover in this course in a theoretical way. But you can see their interconnect technology. These are called eye diagrams to show the, let's say, quality of transfer in interconnect. And this is NVIDIA's proprietary interconnect technology called NVLink. You can see that they've actually been improving the bandwidth quite a bit over here. I cannot read. Okay, I think that's over there. 1.1800 gigabyte per second total, right? That's off a single GPU, I believe. And the reason they're doing this is because a single GPU is not enough to actually do, for example, machine learning inference, because models are huge. So you have to actually have multiple GPUs. But if you have multiple GPUs and they're connected to each other with very shallow interconnect links that don't carry enough bandwidth and have high latency, then your inference performance sucks. Right? And this is, well, because the models are growing a lot, as you can see. You'll see this multiple times. You've probably seen it. It's a bit crazy, I think. I think people should take a step back and figure out how to do these things more efficiently. But this is how it is currently. They've actually invested a lot in the interconnect technology. We're going to cover interconnects probably in the later parts of the course, although we may do some reshuffling of the interconnects. And over time, they've actually improved the interconnect technology quite a bit, I think. These are all well-known interconnects, by the way. It's not research in the end, but the way they designed it, I think this is the latest one. They have 36 GPUs over here and 36 GPUs over here, and they have all-to-all connections through the interconnect. So it's good to think about computer architecture as the entire system, right? And never underestimate the importance of interconnect and memory. When we talk about memory, we're also going to talk about, is it the memory or is it the interconnect? That's the bottleneck. I would say both. And sometimes it's very hard to distinguish between them, because part of memory's function is to store data, but part of memory's function is to communicate data also. So memory is actually very interconnect bound internally also. Here, the interconnects are here for communicating data, but you could also have memories, intermediate memories over here. So you can mix and match memory interconnect quite a bit. So hopefully this course will open your eyes. If you've taken a computer architecture course in the past, it's all about the processors, right? I try not to do that in my course in DDCA, but it's good to think about the world that's outside the processors as well. And even within the processors, we will see that a lot of it is interconnect and memory. Okay, so this is another interesting chip that people have built. How many people have seen this? Okay, not everyone. So these chips are a lot of people. These chips are this big, basically. It's a wafer scale. This is not the latest generation. This is also not the latest generation. I think this is the latest generation, but I'm going to get to that. But you can see that comparatively to the largest GPU, this is huge. This is an entire wafer. Normally, when you fabricate chips, you take a wafer and you cut it into pieces, and then each piece is a chip. These folks said, no, we cannot do that. Why can we not do that? Our target is machine learning inference and training, actually. They start with training. I think they're more pivoting to inference right now, which makes sense. But basically, they said, our workload is too big. If we have two small chips, we cannot have enough memory and computation at the same time on the same chip. Instead, we're going to build a wafer scale engine where we will distribute the computation and distribute the memory, and we will have enough memory, hopefully, to do the inference. Oh. And you can see the numbers over here. This is their latest engine, I think. It's still large silicon, 4 trillion transistor. Now everybody labels their cores AI cores. It's good to also take a step back as a scientist and say, okay, what is marketing and what is not marketing, right? This is marketing, clearly. It's not an AI core. It's actually a SIMD engine, single instruction, multiple data. And then, yeah, I mean, I think I will mention over here the 44 gigabytes of one chip memory. This is very small still. Even though this is a huge chip, this is SRAM. SRAM is very wasteful in terms of space per bit it occupies. As a result, in this huge chip, they have only 45 gigabytes, which is not bad for SRAM. But if you really want to have a model that's, I don't know, not even 1 terabyte, right? 400 gigabytes, then you need to have 10 of these, right? At least 10 of these. So in the end, they actually need to connect a lot of these Cerebus chips, just like NVIDIA is doing with their own chips. Right? So just to give you a contrast, like you can buy SSDs that are much smaller, that are on the order of 4 terabytes, or even larger today, right? 64 terabytes, 128 terabytes, right? So it's good to think about this. If you're very much compute bound and your memory is wasteful, you're going to waste a lot of space. And space means money and power. But today we know how to actually do very dense memories at very small dimensions, form factors. can we actually do computation inside those? If we can actually put computation inside those, maybe we can actually do computation much more efficiently in terms of both cost, power, space, etc. And one of the other issues with designing wafer-scale systems is reliability. Like you can have a fault somewhere, and it's more likely to have faults in a bigger chip than a smaller chip. And you need to have mechanisms to route around the faults. And people are actually doing research in that, and people actually they have built some things inside there, but you need to deal with that much more aggressively. Okay, so there are many other chips that people are designing. Not all of them are AI ML chips. Some of them are actually networking chips. For example, large companies like Amazon design networking chips to enable their infrastructure to be much better. But it's very fascinating that these system companies are taking this cross-stack approach right now. They're designing their chips and they're designing the software together with those chips. And I don't want to bore you more, but you can learn more about it. Okay, more forward-looking. There's also interesting things. You're actually in a lucky time in 2024 because some of these things happened more recently. People are also designing computation mechanisms inside the memory chips. So this is a French company in Grenoble, RowHammer. We're going to talk about that later on and other things as well. But basically, they put a general purpose processor next to each bank in DRAM. This is your regular DRAM, and you can have a processor inside there. This is fascinating. This was not there before 2019. And we've actually done a lot of studies on this, so we're going to cover some of these. And you can also start reading papers about it. You can buy this system, and you can actually do your own experiments. And if you want to do experiments, you're going to have a lab on this. You're going to program this machine in one of the labs. Okay, I'm going to skip these. There are also other things that you can do today. You can have FPGAs that are connected to high bandwidth memory tightly, just like GPUs are connected to high bandwidth memory. But with FPGAs, you can change the logic. So you can specialize the logic to the computation that you're doing. I think that's very interesting. And we have done a lot of studies also in this topic and shown significant benefits by offloading computation to an FPGA that's near a high bandwidth memory, as opposed to doing computations in a general purpose GPU. We may talk about that later on. And also major companies like Samsung have also been designing DRAM to do computation. They essentially put accelerators next to each bank where the accelerator can do matrix vector multiplication. So they can speed up matrix vector multiplication without moving the data out of the DRAM chip. So this is also fascinating, as you can see. Again, we're going to cover some of these later on. There are also other systems that are like this, where you have a lot of memory and you have a buffer chip over here, which has an FPGA, and you can do computation in the buffer chip, and you don't need to move the data outside of this module. So the host system is connected to this module with some motherboard, for example, but now you can actually do, for example, recommendation inference computation. This is a system that Samsung and Meta built together to do that. And other companies are also doing similar things. This is SK Hynix, and they also write other papers. I'm not going to bore you with some of these, but it's fascinating that people are doing this today. And even companies that don't normally do DRAM, like Alibaba, they built their own DRAM chip to do recommendation inference. Essentially, these systems are similar in the sense that they have processors next to each bank. I should say accelerators next to each bank, because these are not complete processors. But RowHammer has a complete processor. Okay. And more recently, people have figured out how to do better interconnect interfaces called Compute Express Link. What this enables is a more flexible interface from the host to the outside world, let's say, so that you can offload computation to anywhere. You can offload computation to memory, storage, etc. It enables also other things that we may talk about later. Okay, so this kind of summarizes the landscape. There are also 3D stacking technologies where you can stack logic underneath memory layers, and you can do computation and customize that computation to the application so that you don't need to move the data away from this chip, right? Okay, we do a lot of work on genome sequencing and analysis. I'll cover some of these, but in all of these, in the end, we must really take an expanded view of computer architecture. As you can see, I've given you a lot of examples. The axiom is true in all of these, I think. All of these companies, and I think going forward, more and more will be designing their own systems across the stack. Okay, this may be a good time to take a break. What do you think? Yes, unless there's a burning question, let's take a break for 15 minutes, and then we're going to pick up from here. Okay. Let's be back at 2:30 to be precise. Yes. Yeah, let's move it either there or here. Which one's better? This is still not good. Let me see. Well, I have to look at it with the. Well, it's too small. Yeah. Very quiet here. I guess it's time. Almost time. Okay, well, we can start. Is everything good with the online? Okay, I'll continue. Okay, now that we've covered some examples of this axiom that I think is important to think about, we should also think about what the future should look like. I think one of the things that one of your fellow students brought up is if you specialize too much, what happens if your workload changes, right? And that's a valid concern, right? You bank on this workload and build chips for it. And if the workload changes a lot, then these chips may be useless. So you should really be careful when you specialize. This is a very common trade-off that you need to think about. Do I use general purpose systems or do I use special purpose systems? And there's a lot of interesting things to think about right now for how specialized should your chip be, right? If you look at a GPU today, what they have done is it was graphics, but they figured out that that graphics engine, the shader cores, are actually programmable single instruction multiple data units, where each instruction really operates on many data elements. So they exposed it to the programmer, and the programmers figured out how to take advantage of those data parallel cores. And that actually helped some of the machine learning workloads. But then over time, machine learning workloads became much more intense in their requirements. So what the GPU started adding are specialized units internally inside the GPU called tensor cores. These are essentially matrix vector multiplication units, just like other people are doing systolic arrays. They are something like this inside the GPU. But they didn't get rid of the general purpose part, right? The general purpose part is still there, but then there's a special purpose part, which is tensor cores, and they have huge high bandwidth memory that can provide very high bandwidth to those cores. So in a sense, the approach that was taken over time with that sort of hardware was it was special purpose, it became general purpose, and added more special purpose elements internally. So there's a lot of special purpose versus general purpose mix going on inside a GPU system today, which is interesting. But if you're doing just a systolic array, that may not be general purpose enough, right? So it's good to think about this. Okay, we may cover some of these other architectures later. And this is another example of trade-off that we will cover in architecture, right? As an architect, you have to make that decision, right? But as an architect, you should also imagine the future. That's also important. And we should always ask the question, what kind of future do we want? And this is going to set some of the stage of what we're going to discuss in the next lectures. And I like thinking about things that are other infrastructure. Today, we're building infrastructure. Computing is an infrastructure, but people have built infrastructure. We're not the first people under the sun to build infrastructure, right? This is infrastructure. This is a bridge. Do people know where this bridge is? Okay, that's a good guess, but wrong. Anybody else? The Cohen arrows, that's good, yeah. Okay, very good. Did you get any inspiration from the source? There's a side channel over here, but I don't think you can read that. So side channels are important, right? This Tacom 1 PNG. Yeah, it's a Tacoma and arrows bridge. But unfortunately, it doesn't exist anymore. So your answer is kind of wrong also, but I'm just kidding. That would be nitpicking on the question. So this is what happened to it. A bit flip, and this bridge fell. And this is a robustness problem in the end. It's a reliability problem, availability problem, safety problem, and also a security problem. And this is another beautiful view. There are videos of this also. There are these people on a rod over here, constructing, I believe, in New York over here. And they're very happy right now, but if a bit flip happens on that rod, they may not be very happy, right? So we should really think about robustness. I have security over here, but I think you can generalize this with robustness. I think in the systems we design going into the future, we're going to have infrastructure that's much more common than these infrastructures and then these infrastructures, right? And these infrastructures will try to make decisions for themselves. So we need to really design them to be robust. And I think robustness, one way of defining robustness is really preventing unforeseen consequences. This is a very general way, but I think this is a very good thing to strive for because there will be unforeseen consequences in things like this. For example, if you train this thing, and if it's in a situation where it cannot really reason about, and it tries to parrot what it's trained on, is it going to be good? That's always a good question. And we've seen many situations where it's not good, currently at least, because it's designed on non-flexible decision-making mechanisms that are purely trained based on training data, right? And then there's even worse situations potentially when we go outside, when we deal with the unknown, then we'll need to deal with a lot of things that are unforeseen, space, for example. Okay, so I think a big challenge for designing computing systems is robustness, reliability, security, and safety. That's going to be much more important in the future, in my opinion. And we're going to talk a lot about in this course from memory perspective, for example. There's a lot to discuss over here. In fact, one could design a dependable systems course that I would like to teach at some point, but I cannot teach 10 courses. Then I will have no time for anything else in the world. Yeah. Okay, I think we should probably, anyway, okay. So what other things? What kind of a future do you want? Do you want a future that looks like this? Or do you want a future that looks like this? This is 1930s Pittsburgh. I used to live there. Not in 1930s. Not in the 1930s. I was there in a much better time. But I think we want sustainability and energy efficiency, and I'm going to take this as granted because, yeah, otherwise we'll be in big trouble. But hopefully we will see that we need to rethink our computing systems to be much more sustainable and energy efficient going into the future. And then we of course need to solve a lot of problems, right? We have created or maybe exacerbated the problem of climate. And we have clearly created problems of congestion. And there are some other things that are in nature that we don't understand, like intelligence, how this thing works. These are very complex things that require a lot of power and performance, right? And public health. And then genome analysis. This is an area that we work on. And we're going to have a lecture on this topic also. Again, this is an area where data is growing so fast because of the improvements in underlying technology that its analysis is challenging, its efficient analysis challenging. Yet, if you can actually efficiently analyze the genomic data, you can really unlock a lot of advancements in both medicine and health and also science. You can understand species, evolution. You can predict what you're dealing with in a sample. You can predict whether or not you will have a public health disaster, for example. You can you can do surveillance of outbreaks, and you can develop personalized medicine. So there are many other applications. So this is an area that we do work on, and we're going to cover some of this. It's a fascinating area, in my opinion, and we've been writing papers about it. If you're interested, you can look at any of these papers, of course, even before we get to it. Okay, as I mentioned, there's a genomics course also. I think it's somewhere over here. Yeah. Okay, we also organize workshops on this topic. So, of course, there's also other reasons for performance, which is machine learning today. That I don't want to harp on again, but clearly memory and compute requirements are growing in machine learning. And this is a talk by Cerebrus's CTO. I had invited him to give a talk in one of the live seminars that we organized a few years ago. And he used a slide where he showed that essentially model requirements are growing in terms of memory as well as compute. And this is the reason for why they justify this large wafer-scale chip. Okay, it's good to look at this picture and think, what kind of a system do we want? Do we want to keep our systems growing and growing and growing, interconnecting bigger systems? And these are not very efficient systems in the end. So a lot of people are actually building data centers around water sources of the planet. And they're really wasting a lot of, let's say, sustainability budget of the planet going into the future. So it's a bit crazy. I spent a lot of time in the Bay Area, and I think it's more crazy than it looks. Okay. Okay, but I think there is some legitimacy to some of it, meaning we need high performance because there are a lot of problems that we want to solve, and there are a lot of tough problems that we want to solve, and we want to solve all of them. We're greedy in that sense. The question is, can we get high performance at high sustainability and high efficiency? Okay, and then there's also, I think, an area that's going to be increasingly important, which is personalization. In a lot of these applications going into the future, we're going to personalize more and more. In genomics, for example, we want to actually, for example, we want to have a device that we could give to people where they can analyze their own genome privately without anybody interfering with it. And they can get recommendations into what to do for a given disease, right? Ideally, if you could put this as much as possible without moving the data out of that device, this could be very useful for both personalization and privacy, right? So you can learn about that person over time for many years, right? Okay, so this is another area that that's the reason why I got into genomics, actually. And there's a lot to do over here, I think. And it's not only in genomics, I think in other dimensions where technology affects our lives, I think we want more personalization, right? You don't want a robot to be not personalized to the person, right? Who they really have been interacting with. Maybe this is the future of education. You're not going to sit here, but you're going to interact with a robot. I don't know if I'll be inside the robot, but maybe robot will learn a model that is based on the videos, etc., and they will make a mess out of it. At least with the current models, I don't believe this is possible currently. This sort of very like primitive ways of learning is possible, but advanced methods of learning, I think with the models we have, in my opinion, is impossible unless we have fundamental breakthrough in the way we design our machine learning models and in the way we look at learning. Right now, I believe we look at learning as a statistical process, but I believe there's a lot more than that. Okay, I digressed a little bit. In the end, we need personalization and privacy, I think, and this is going to be a lot more important in the future. Okay, so why am I telling you all this? Because in the end, all of these actually dictate the requirements and the type of systems we design, right? So the application space, the use cases, really determine how you design the architecture and the system to enable that sort of application and use case. In a lot of these, you can imagine using completely general purpose processors, right? And that's going to be a completely big waste. But you can specialize the system that you use, that you design for different use cases. Okay, I think I've kind of said this before, but just to jog your memory a little bit, computer architecture is really the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. So these goals are really important over there. And we will talk more about metrics. But before we go into metrics, etc., I want to talk a little bit about like why study this. I kind of said this. In the end, we want to enable better systems, make computers faster, cheaper, smaller, more reliable, and also more specialized. And computer architecture is in a very interesting position over here, right? Computer architects are nice in the sense that you can modify both hardware and the software. You're sitting in the middle. And you can exploit, you can look at what's underlying technology. You can see what's new technology that you can exploit. And there are many technologies at the lower levels of the stack that you can take advantage of. And it's like really building architecture. In fact, in some other courses, I use the building architecture as an example. Real architects build buildings and they use different materials, for example, and they use their creativity and also art and also science to build some system that is going to be good for some purpose, right? Some goal. Computer architecture is very similar in the end. You can mix and match the materials underneath. As long as you satisfy your goals, like maybe it could be a cost goal also, it could be a security goal, you can actually exploit the underlying technology. And you can shape the software at the higher level, but shaping the software is always harder, right? If you build a specialized system, for example, if your software needs to change completely, then you need to also build a path to enable that change. It's a lot easier to change the underlying hardware such that it runs with existing software, right? That's been the paradigm, but it turns out it's not easy to do that going forward because software is actually moving very fast also. Okay, enabling new applications and systems is another reason why we study architecture. I think some of these we could not imagine in the past, but for example, visualization has gone a long way with physics processors or GPUs, etc. Self-driving cars, we'll see if it's possible. I think there's more over here. And also enable better solutions to problems is another reason why we study architecture, right? In the end, software innovation is built on trends and changes in computer architecture. Okay, I'm going to skip this because this is not exactly true anymore. 50% performance improvement per year, you hope. So this is one downside. I'm going to talk about that. Essentially, over many years, one of the reasons why we're actually also exploring this across the stack, cross-layer approach, algorithm, device, co-design, and taking an expanded view of computer architecture is because technology is not improving as fast, right? In the past, we were in a regime where you reduce the size of the transistor or you reduce the size of some hardware component, transistor, you get better energy, lower voltage. That has been gone for almost 20 years right now. This is called Dennard scaling. Bob Dennard, who is the inventor of DRAM, also posited the scaling laws. And he basically said that over time, as you reduce the size of the transistor, you can reduce the threshold voltage to activate things, and also you can reduce the energy. But that has stopped because we reached the limits, physical limits of that, which means that as you reduce the size of a transistor, you're not getting more efficient. And then there's also another scaling. This means that you're also getting lower performance. You're also not getting as high performance as you have, right? So this actually pushed people to do more innovative things from an architectural perspective, right? Technology scaling, reducing the size of the transistor is more of a device and technology type of improvement, and manufacturing type of improvement also. That's why these folks who manufacture chips are dying one by one, because it's very difficult to improve the process to reduce the size of a transistor so that you can pack more transistors while keeping other qualities like reliability, energy, performance, etc. Okay, there was another scaling trend, which is Moore's law, which is, I think, still holding a little bit. But essentially, when you reduce the size of the transistor, the cost of a transistor is also reducing. Right? Over time, this reduced a lot. I think we're in a curve where the cost is reducing much more slowly than before. In fact, the cost may be increasing at some point because the investment that you need to make to reduce the size of the transistor is shooting up right now. That's one of the reasons why a lot of these players that used to manufacture chips have dropped out. There are only 2 players, I think, who are doing advanced manufacturing today. Yeah, so this is another technology-driven reason why architecture has become a lot more important, just to give you a historical perspective. Okay, so that 50% performance improvement was true at some point, but it's not as true. But higher performance improvements are possible if you actually rethink the stack, right? If you actually rethink the architecture. I'm going to show you a lot of results starting, I think, maybe tomorrow, maybe not tomorrow, maybe starting next week, where we will talk about processing in memory, for example, where we will see improvements of 100x performance, and also at the same time 100x energy on graph processing workloads, for example, if you do processing in memory for graph processing. So if you specialize somewhat the architecture to graph processing, you can get 100x plus 100x, but it takes time. You need to change the entire stack. Okay, another reason to study computer architecture is understand why computers work the way they do. Meaning, even if you're not going to do anything enabling better things, you may actually still do something interesting. If you understand why computers behave the way they do, you can actually design much more efficient software, for example, or much more efficient systems in the end, even without changing the architecture. And there are a lot of people who work and do software optimization, for example, by understanding the computers in a really nice way. There are also a lot of security people who understand why computers work the way they work, and they figure out different side channels. They figure out there are different ways of extracting data out of computers, even though the computers are not willing to give them that data in a nice way. Okay, so I think it's a very exciting time to study computer architecture today. Clearly, there is a huge paradigm shift to novel architectures. Even processing in memory is being examined, as we discussed. I think I've already kind of covered some of these, but there are many difficult problems over here: applications, power constraints, complexity of the design, difficulties in technology scaling, which we just talked about, memory bottleneck, which we will talk a lot about, reliability problems, programmability issues, security and privacy issues. These are some of these are motivating the shift. Some of these are caused by the shift. For example, if you change the paradigm, programmability becomes a problem. Right? Whereas if in the old paradigm where we were designing general purpose CPUs, programmability is not an issue. Everybody writes a single threaded program, and hopefully the general purpose CPU becomes better and better and better over generations. If that stops now, you need to change the paradigm such that, oh, I design across the stack. Now the programmer needs to do different things. Even move from CPUs to GPUs was not, or I don't think it's complete yet, but is not easy, right? Because CPUs are single-threaded, GPUs are multi-threaded, and each thread in a GPU is, well, multi-threaded, bundled together such that it can do SIMD execution. It's called SIMT, single instruction multiple thread model. Even that shift is not easy, basically. That's a different programming model. And whenever you change the programming model, adoption becomes an issue in hardware. We're going to see this a lot also. And this is going to be a lot more important than processing in memory and processing in storage. So Geraldo will tell you about some of the programming mechanisms, hopefully. Okay. So just, again, I like picking on Geraldo, as you can see. A senior PhD student who's graduating, doing a lot of great work, requires some picking. But you will see certainly some talks from, cutting-edge talks from my students in the group, and maybe some invited seminars also from people in later parts of the course. where we will discuss some cutting-edge research in some of these areas. Okay, in the end, I think there are no clear definitive answers to the problems. Just to show you the impact of these problems affect all parts of the computing stack. There are many new demands from the top. I actually have a different way of computing stack where the user is, as you can see over here. There are many new issues at the bottom, technology scaling type of issues. So an architect's job is not easy in that sense, right? If you're designing a computing system, if you're an architect, you need to consider what's coming up. You need to look up. You need to look down. You need to consider what's going down over here. What are the technology scaling? What technology issues are you dealing with? If I design this using DRAM and CMOS technology, what am I going to deal with, right? If I choose some other technology like RRAM, phase change memory, what am I going to deal with, right? So, and the top is actually even harder because that thing can change. You design a system today, it's going to be used 5 years down the road. Is it going to be the same applications that are going to be executing, right? That's why architecture is actually a fascinating area, but also it's a tough area. You need to make these decisions. And also it's not a perfect science in that sense, right? Because how do you model all of these to get certainty, right? You cannot. So it's really part of the art. So you really need to make gut feeling type of decisions sometimes, of course, guided by some scientific modeling and also as well as experience. And also, I think people should not underestimate the users, because especially if you're designing systems that are user-facing, like mobile phones, etc., people have fast-changing demands and personalities, right? So you need to look up to that also and understand that if you want to cater to that. So in the end, there are no clear definitive answers, and that's why it's good to study this topic. And as I mentioned, computing landscape is very different from 10 to 20 years ago today. A lot of these, both software and technologies, have been changing. And you need to look both forward, so both up and down, and forward and backward. Okay, I think I already said this. So in the end, this is a good thing. People are really re-examining everything, every component and its interfaces. For example, I don't think people would have imagined a GPU company doing their own proprietary interconnects today, which is really happening. But if you actually went back 10 years ago or 15 years ago, that would not be imaginable, right? So a lot of things are changing today. And that's not a given in the end. If the workload changes maybe slightly, maybe someone figures out a much better way of doing machine learning than the current terribly wasteful way of doing machine learning, maybe this is going to go away, right? That's not a bad task to take on as a researcher or an entrepreneur. Okay, I think I've already given you this axiom. Any questions? Don't leave your questions to the break. No, we still have some time. Okay, let me just give you some historical perspective also. So I'm giving you this picture, right? This picture is actually very interesting because people have picked on it in different ways. But I believe there's a lot of opportunity at the bottom also. So right now, I think at least some people, which I'm going to mention in another slide over here, think that the opportunities at the bottom are actually lower. But I don't think so. I think there's a lot to investigate at the device level to really understand what new technologies could be much more efficient and effective. These could be, for example, some superconducting technology, right? That could be enabled. Even though it may be out there, it may take some time. It's good to examine it. More efficient memory technologies, for example. I think it's really good to invest in that. And I think this sort of thing enabled a lot of things. This is there's this quote: "There's plenty of room at the bottom." I don't know if anybody heard of it before. Maybe not, but maybe some people. But this really refers to a talk that was given by Feynman, who was a famous physicist. How many people have read Feynman's lectures on computing? Maybe not the computing, but the physics. He also has lectures on computing, which are actually really nice. But anyway, this person envisioned that, basically, he said that we should really be investigating opportunities at the nanoscale, at the very low level, so that we can manipulate, for example, individual atoms. That would be nice. I don't think we're still there yet, but we're getting close, actually. If you look at flash memory, it's a technology where you can really change the currents and voltages such that you really manipulate very small number of electrons to store data. DRAM is also getting to that scale, but it's hard to control. But basically, in this talk, he said that if we enable this, we can actually enable much better chemistry, etc. And he also was interested in much denser computer circuitry with these very small nanotechnology. I will call it nanotechnology. I think people later call this nanotechnology, if you will. Although nano doesn't do justice, right? Because I used to be part of this gigascale systems research center. And this was 2008, 2009. What is gigascale today? Everybody's doing gigascale, right? This is much powerful than gigascale. So today we're even higher than exascale, etc. Right? So these numbers, it's always dangerous to use a number as a term to define something into the future, right? Nanotechnology, I think, is kind of, you need to think about in a lower terms. But basically what he was interested in is really to, for example, have nanoscale machines. Nanoscale machines where you can arrange the atoms the way you want and do chemical synthesis by mechanical manipulation. And he also presented the possibility of the swallowing the doctor, which is very interesting, right? So it's a surgical robot, essentially. People are trying to do these things right now, but all of these are really enabled by lower level technological improvements, right? And I think we should take more advantage of that. And I think more recently, people have written kind of the obvious also, which is really there's plenty of room at the top, meaning that if you actually are not scaling at the technology level, you should focus a lot more on the top, which is what's happening anyway. I think this paper is a nice description of what has happened, as opposed to what should happen, because what should happen is obvious, and what's happened, it's happened anyway, and it's going to happen anyway. But basically, they've said that we should focus more on the algorithm, software, and architectural layers, because technology is not going to improve as much. I disagree with the latter part, but I agree with the first part. I think technology is going to improve also. Believing in the technology is always good, and investing in the technology is always good. Of course, technology will not improve if you don't invest in it, right? If all you say is, oh, technology is not going to improve, so let's not improve it, you're guaranteed that technology is not going to improve. This is a mindset issue, as you can see, right? It's also a self-fulfilling prophecy. If you know that term, it's in psychology. Basically, you believe that something will happen and that thing will happen, and that thing could be a negative thing. And in this case, if you believe and act that something will happen, you guarantee that that thing will happen, meaning technology will not improve. Okay, but I think that we need to revisit this axiom also. And in this course, I'm going to also set hopefully this mindset where I believe there's plenty of room both at the top and the bottom, but you can enable much more so when you communicate well between the top and the bottom. Right? I think that's one problem we have in existing systems. You don't communicate very well, even though nothing improves in top and the bottom. If you actually communicate more information in between, you can actually get a much better system. We're going to talk about that also. This is more optimizing across the stack. Yeah, I think I'm going to show some papers later on that talk about this. Okay, any questions? Okay, let me cover a little bit more. We still have a lot more. We're going to switch to memory soon, but I think I'm going to talk about memory. But before I talk about memory, I think it's really important to think that I would like you to think about this course to be questioning what limits us in designing the best computing architectures for the future. We're going to learn about what's current, but we should always look for the future. So it's always good to have a critical mindset as to what is the problem with what's current. And hopefully we'll provide some directions for fundamentally better designs, and maybe there will be newer ideas in this course for other designs. And I will advocate some principled approaches. This is important. The principles may appear after ideas. So this is actually interesting also. In scientific progress, you have some principled thinking and you develop some ideas. But sometimes you, and that those ideas are, let's say, commensurate with the principles. But sometimes you are just creative. Again, you smoke pot or whatever. You come up with some creative ideas. And then this may actually not fit any principle, but then the principle may come later, right? It's always good to think about that also. So there are multiple ways of enabling innovation. One is really very structured principled thinking, and the other is more out of the box thinking where you don't have that structure and principled thinking, right? Okay, so I think what is going to limit us into the future a lot is demanding applications, but it's not going to be, we're not going to be out of them, right? Well, essentially, people are dreamers, people dream, and applications will come. We have not, people have not really, I think, predicted the machine learning revolution, if you will. It's happened. People have not predicted other applications, and it's happened. This will always happen, I think. As applications push boundaries, computing platforms will become increasingly strained and constrained. And This is not going to end. We'll always have more applications to deal with. In fact, I think people have made the mistake of saying weird things or things that sound stupid right now, right? Who's ever going to need more than 640 kilobyte of memory, right? Or at some point when people designed the MIPS R2000 processor, it's a beautiful processor, but it's very much simpler compared to what you have learned in DDCA, for example. And they said basically, oh, this is the best processor. We don't need anything other than this. We just should optimize this. Yeah. So basically, I think people will always be wrong if they think it's the end. So I think one of the things that we will focus on in this course early on is this key realization. I'm going to give you the key realization. I think you're waiting for it. So basically, I think the key realization is that modern systems are bottlenecked by data storage and movement, memory and communication, if you will. So that's why we're going to put a lot of importance to this in this course. And that's how I will transition to the memory part of this course. So we're going to focus a lot on data storage systems, especially memory, but we're going to also talk a lot about interconnects and storage. So hopefully we'll have more lectures early on. We may shuffle the lectures in this course a little bit compared to last semester or the previous semester. So you may see a different ordering. Let me give you some data and examples. By the way, should we take another break? Let me see. Anybody wants a break? Okay, I think yes or no. Okay, so let's take another break for 10 minutes because this is going to change the topic a little bit. Let's be back at 15:12, 11 minutes actually, and then we can continue. Yes, hey. No. We can get started. Is everything okay online? I should check. This is called online testing. While you're online, you keep testing whether the thing is correct or not. It's going to be increasingly more employed in real systems. So while the system is running, you do some online testing. So if you have a chip, for example, once in a while you test the cores internally to make sure that there is no data corruption or there's no problem. You can increase the voltage, increase the frequency to make that testing more predictive of future failures potential, or increase the temperature if you can do that. We may talk about that. But this is what we're dealing with technology today, basically. And things are not reliable, and one way of actually dealing with that reliability issue is testing once in a while whether things are going fine. The key is, of course, how do you do it with low overhead and low energy overhead, performance overhead, low area overhead, low overhead in general. But this is something that was envisioned like 15, 16 years ago. In fact, we have some papers on this topic as well. But this is being incorporated into the real CPUs and GPUs today because things are much more unreliable today. Okay, anyway, I changed the topic, but that's how it is. And we'll see more of that increasingly in the memory controllers too. Okay, so basically we're focusing on, to begin with, in this course, we're going to focus on data storage systems and specifically memory, although we're going to treat memory and storage as not just a continuum, but maybe something that needs to be considered together at the same time. And if you look at main memory, this is just a picture, of course, one picture. Main memory is really there for all components, right? Server, mobile, embedded, desktop, sensor. Almost all of them have main memory. And things that don't have main memory suffer in general. They don't scale very well, etc. They're extremely costly because they're based on SRAM, for example. We kind of discussed that with Cerebras, for example, right? Cerebras has this huge SRAM and they connect many of these Cerebras chips. And I don't think they have a good story for main memory yet, but I think that's a bit suffering. In the end, almost all systems have some sort of main memory. And main memory system must scale in many dimensions to maintain both performance growth and technology scaling benefits, like size, capacity, or technology, efficiency, cost, and algorithms we use to manage it. So there are many dimensions of the memory itself. And again, memory is there not just for general purpose processors that look kind of like this, but also FPGAs, also for GPUs, also for accelerators. So it's there. Maybe not all of them, but some of them. Okay, so that's what we're going to focus on. But I think I want to spend today and hopefully a lot of tomorrow on why is memory so important, especially today. And I'm going to cover some of the trends in memory and put some data on the trends also. So I'm going to give you multiple different perspectives. One is performance, important, energy, scaling and robustness, which we have discussed, reliable, security, and safety. After giving these perspectives, we're going to cover some of the trends, challenges, and opportunities, as well as solution directions. And then we're going to spend, I don't know how many lectures, but a good chunk of the first half of the course on memory systems in general, focusing on different issues, like how to solve these problems in different ways, processing in memory, looking at robustness problems, looking at how to reduce the latency, for example, looking at how to reduce the energy, etc. Does that sound good? Exciting? Okay. Okay, and in all of these, I think I should say that before we jump into it, there's a lot of opportunity for further improvements. So this is a ripe area for doing research as well as development. Okay, well, I'll start with this picture. This is an old picture. I actually drew this picture in a program called Xfig. Has anyone used Xfig? Wow. It doesn't come with like Linux distributions these days, Xfig? Okay, maybe they have updated to a much better one. But basically, this was my first proposal that I wrote to National Science Foundation in the US when I was a budding professor at Carnegie Mellon University. And I basically said that, the system today looks like this. You have essentially a bunch of cores in a system, and these cores share a huge memory hierarchy. In fact, most of the chip is the memory hierarchy. There are caches, there are interconnects, there are other caches, there are other interconnects, there are memory controllers, there are other interconnects, and there's memory and other interconnects, and there's more memory or storage. And essentially, most of the system, if you look at a single node, is dedicated to storing and moving data. And the reason I drew this picture was to show that, these different cores interfere with each other when they access the memory system. And we want to build much more predictable systems that provide quality of service to the users. such that if you don't want to be delayed in a task, for example, other cores that are not important potentially for that task should not delay you. And how do you design a memory system that's scalable and quality of service aware like that? But I'm going to use that same picture for another purpose right now. If you look at this, actually, if you do the calculations, more than 95% of the node area is dedicated to storing and moving data. Cores, which is where computation is done. It could be an accelerator also, essentially. In fact, it is a very small fraction of the chip. Now, you take this picture, and in a reasonable world, you ask the question to a 10-year-old, saying, I'm dedicating almost all of my resources to data storage and movement components. This should not be a bottleneck, right? And a reasonable 10-year-old probably would say, yes, you already did a lot, right? But yet, the system is still bottlenecked by memory, right? So I think we're kind of going against reason here. Of course, it's not a proof what I just provided, but it's good to think about with a blank slate. What would a 10-year-old think about what we're doing in our systems today? This is kind of a critical thinking, actually, right? Okay, so basically, the problem is really we're bottlenecked by data, and the processing is really done far away from the data, and as a result, we're building all of these hierarchies over here to overcome that data movement bottleneck, to reuse the data as much as possible, but we're still bottlenecked by data. So I'm going to give you some more results. Essentially, the reason is important workloads are all data intensive, and they require rapid and efficient processing of large amounts of data. On top of this, today, data is increasing. We can generate more data than we can process, and we want to perform more sophisticated analyses on the data. So yes, computation requirements are growing, but memory requirements are growing even faster, arguably. Well, not arguably, actually, depends on the domain. That's why we have this picture over here, where both memory and computation requirements are growing, as you can see over here. But people are doing something about computation. In one of those pictures earlier in the GPUs, for example, people have figured out how to do computation with smaller precision, right? We're going to talk about that maybe later. Smaller precision computing is becoming more popular because it reduces both data movement as well as it reduces the complexity of your processing units, right? So if you can actually operate on data types that are not 32 bits, but 4 bits, or even 2 bits, or 1 bit, then you're much better off. This reduces your precision, but this may actually affect your accuracy. But if you can do it in a way that doesn't affect your accuracy by rethinking your stack, you can actually have a much more efficient system. So in all GPUs, they used to have 32-bit floating points, and that was a big thing. And then they reduced to 16-bit, and then they reduced it to 8 bits. And right now, they actually reduced it to 4 bits, and with some multi-scale, meaning the ability to scale the floating point computation also to different data bits. Okay, so memory is essentially critical for performance. There are a lot of papers that show that. I'm going to give you some more data on this, but essentially, it's not just machine learning. This picture is to show that there are many other workloads that we care about that are important, and they're bound by memory. They're bound by different things in memory, and sometimes all things in memory, like memory bandwidth, memory capacity, and memory latency. All of them really affect the performance and energy efficiency. And we've done a lot of studies on some of these workloads, as well as some of these mobile workloads. And clearly, these workloads are some things that we're exercising right now. I think we're exercising some of these on YouTube when this lecture is processed. There are some machine learning frameworks that are running also. And some people are actually using the web browsers to watch these lectures, right? So we're exercising all of these workloads right now, I think. And they're all bottlenecked by data in the end. Okay, genome analysis is going to be is even more bottlenecked by data. We have a lot of results that show that. I will put some data to all of these claims later on. And genome analysis is very interesting because we have some of these devices that can actually generate a lot of data. This is a paper that we wrote several years ago. This is a nanopore sequencing device. It's actually very powerful. It's very low cost. And because of the technological improvements, people were able to sequence DNA at both low latency and high throughput using these devices at low cost. And this has enabled an explosion of data in genomic data. And by the way, this has actually enabled a lot of interesting studies for COVID, et cetera, because it's very fast, et cetera. But the fact that this technology is scaling very well and computer analysis technology is not keeping up is a problem. So they're very good data generators today. That's my point. This is a data generator today. And that's what's really bottlenecking us, the way we currently design our computing systems. So let's take a look at some of the trends in the memory system. So there's some recent technology, architecture, and application trends that lead to some new requirements and they exacerbate old requirements. I've already given some of the application trends, right? Data is increasing essentially, and the requirements are increasing. We've always demanded a lot from memory. So memory system, people knew the importance of memory system, but it's getting much, much more important today. We've been arguing and we've been doing a lot of research showing that DRAM and memory controllers, as we design them today, are unlikely to satisfy all of the requirements. In fact, they're falling very short, and they're going to be even worse into the future if you don't do something about it. Some rethinking of the system. And also, there's some emerging memory technologies that are quite interesting. It was phase change memory at some point. It's less interesting at this point, perhaps, but there are other technologies that are quite interesting that enable other opportunities. So if you have an emerging memory technology that's almost as fast as DRAM, for example, but that's non-volatile, meaning whenever you plug it off from power, you don't lose the data, then this may actually change the way we program the system and we design the systems, right? You can actually have your persistent data directly manipulated on this memory technology as opposed to being moved to DRAM or even SRAM, maybe. You can actually have some of this emerging technology on chip, on the processor chip, even if you keep the processor-centric paradigm. So there are a lot of interesting opportunities. It's still good to examine a lot of these. So I think we need to rethink the main memory system, given all of these that's happening at the technology level, architecture level, and application levels, to fix the issues we're having with dominant technologies we have today. Well, dominant technology we have today, not plural. There's only one. But it has different kinds of technology, like different types of DRAM, as we will see also, and enable some of these emerging technologies while satisfying all the requirements. So let's take a look at some of these major trends. Essentially, we need more and more from memory, all aspects of memory. We want more capacity because data is increasing, more bandwidth because our need for accessing a lot of data concurrently is increasing so that we can process these, for example, large machine learning models, or we can process many requests from many different users in a database, right? And the need for quality of service is also increasing because we integrate many more components on a chip, many cores. And these cores may be executing different types of workloads, right? In fact, in an SoC today, there are different types of workloads. In my pocket, this thing can actually execute many workloads concurrently on the same SoC, right? And they're all sharing the main memory. They all go through the main memory. Okay, at the same time, energy and power is a key system design concern for both the entire system, and main memory occupies a big chunk of it. And also at the same time, the technology that we design our main memories with is not doing well in terms of scale. So we're going to cover some of these, and this will kind of motivate the different perspectives that I mentioned over here. Let's look at this performance type of perspective first. Clearly, I mean, I think I've kind of said all of these, but applications are increasingly data intensive. We can put many, many agents and cores in the same chip or multiple chips. Today, everybody's very excited about chiplets, for example. In my opinion, chiplets are very interesting, but they're not that interesting in the end, right? They're just putting together multiple chips in a better interconnect technology. It's a way of scaling the system. This just exacerbates the problem, basically. You can have much more cores and agents and accelerators in the same area or in a bigger area. And then people want to consolidate in many different domains, cloud computing. You want to execute multiple applications together so that you don't want to waste hardware. Right? Actually, wasting hardware is bad for efficiency and cost. But there's also another reason why wasting hardware is bad today that people didn't consider a lot. Sustainability, for example. If you waste hardware, that means you need to produce more hardware to accommodate the workload. So your efficiency actually directly affects your sustainability in the end. So sustainability is affected by many things, not just energy, but also wasting hardware and whether or not you can recycle the hardware, right? So if your hardware stays the same and you don't over-provision, this is good for sustainability. And you can use it for thousands of years without having to dump it somewhere. Then that's good, actually. Okay. So this is just one picture. This is a relatively old paper from HP Labs in ISCA 2009. Where these folks show that core count is doubling approximately every 2 years, whereas memory capacity, DRAM, DIMM capacity is doubling approximately every 3 years. This is because it's easier to scale logic than DRAM. These trends are even worse right now, maybe, it depends. like the disparity is even worse, I should say. Essentially, these folks show that memory capacity per core is expected to drop by 30% every 2 years, assuming all of these numbers are correct, which has some error margin, of course, always, right? And this is not good, clearly, right, for performance. What do people normally expect? Whenever you buy a new system, you should not lose performance. But if you actually have less memory, you lose performance, or waste some of the cores. Right? Meaning, if you want to get the same performance, you don't want to populate these cores with things that are running. So this is not a good trend in that sense. And trends are actually much worse for memory bandwidth per core. I'm going to show that in a different way in the next slide over here. So this is a fun slide to cover. We recently revisited the slide. I'm going to show you the revisited version, but I'm going to show you the old version first. So these are common DRAM technology, DDR, for 18 years or so, as you can see. And this specifies the improvement. And when you look at memory, in general, because of the processor-centric mindset, when people design memories, the thing to optimize for is cost. And cost means capacity per area. How many bits you can squeeze in a given area. So people try to maximize this as much as possible, right? And that's the metric that's the most important in designing memories today. This is also the not memory-centric mindset, right? It's really treating memory as dumb storage. It just gives you data with as little money spent on it as possible. And this has improved by a lot, as you can see, in these 18 years, under 28x. So it's not bad. Memory bandwidth, I'm going to give you that one also and then ask you the latency. Has improved, not bad, 20x. But this is DDR technology, so this doesn't change the interface as much. We're going to talk about 3D stacking technologies where you have more parallel interface to memory, such that you can access many banks concurrently and also increase the frequency of access. So you can actually increase this bandwidth more, but you need to pay more money. So in general, if you want to increase bandwidth, you need to pay more money. You can do it. Now, if you want to increase latency, you need to pay even more money. Well, I didn't ask you, sorry. But this is the sad state of latency, meaning it has reduced by only 30% during these 18 years. And this is in part a design choice, in part a mindset issue, in part a business issue, etc. And also in part, technically, it's much more difficult to reduce latency in general. And this is actually very interesting to look at, basically. Reducing latency is in general much harder than providing higher bandwidth, which is much harder than providing higher capacity, assuming your technology is scaling nicely. So this is what's been happening in these 18 years, as you can see. And this is still, so latency, we're going to talk a lot about latency because reducing latency is really important in the end. So we're going to talk about covering the latency with more bandwidth. So that's what GPUs do, for example. They actually have many threads. With many threads, your memory could be long latency, but hopefully you can tolerate that latency, right? Your program can still make progress because you parallelize your program nicely and you don't see that latency, hopefully. This is nice, assuming you parallelize your program really nicely, right? But if there are some latency critical components in your program, for example, if there's only one thread that is doing some task distribution, etc., then you're bottlenecked by that thread. And then your latency is extremely important. You don't care about how many cores you have because that thread is not going to utilize those many cores. Right? This is also called Amdahl's law or Amdahl's bottleneck or the serial bottleneck. Essentially, your performance improvement with a parallel processing is really dictated by how much, what fraction of your program you can parallelize in the end, right? Just to give you numbers, right? If you can parallelize only 50% of your program and not improve the remaining 50%, the maximum speed up you can get with infinite number of cores is 2, right? If you do 90% parallelization, the maximum speed up you get with infinite number of cores is 10. So it's very sad, as you can see, right? You have to parallelize a lot to get a very large maximum speed up. If you do 99% parallelization and only 1% of your program is serial, of course, this is assuming that this is perfectly parallel and there's a perfectly serial portion. The world is not like that, but there are perfectly serial portions. Perfectly parallel portions usually do not exist. There's always issues in the perfectly parallel assumption, which we will cover actually toward lecture 25 or so. We'll get to that also in the more compute-centric parts of the lectures. Okay, if you parallelize 99%, the maximum speed up you get with infinite number of cores is 100. Right? Again, very small number. But it's good to think about that. Amdahl's law is always in effect. People have learned about Amdahl's law, right? Okay, good. How many people learned about Amdahl's law? How many people did not? Don't be shy. Okay, we're going to get to that. We're going to get to that. But basically, hopefully you understood the analysis I made, right? The analysis is how much you can parallelize. You're in the end bottleneck by the part that you cannot improve. It's kind of an obvious thing, but Amdahl nicely put it in 1965 in a paper, and we'll assign you that paper when we get to it. Okay, so going back to latency, I'm saying latency is important, and people usually overlook it, or people tolerate it because this is the way people have treated memories for a long time, right? It's not supposed to be a high performance thing. It's supposed to be a high capacity thing. More recently, it's been changing, right? With machine learning, people have figured out, oh, okay, if we treat it as only a high capacity thing, we're going to have trouble. So I want a lot of bandwidth also. Unfortunately, they haven't figured out how to get high capacity and high bandwidth at the very same time. HBM makes the trade-off that you have 3D stacking of memory. It's much smaller amount compared to a two-dimensional layout of memory. You get very high bandwidth because of the 3D stacking, because you can access the interface in parallel, but you get much lower capacity. So this is always a fundamental trade-off also. Bandwidth capacity, bandwidth latency, latency capacity. There are all these trade-offs in the memory system design that we will examine. Latency capacity trade-off is a very, very strong one. That's why this is very low improvement, and that's why that has been very high improvement, as you can see. It's very difficult to reduce latency, but I think we should really strive for reducing latency a lot more in our systems, because latency is source of a lot of evil, in the sense that because of this high latency, we actually add a lot of complexity to our systems, right? It takes, for example, 100 nanoseconds to access data, whereas it takes, I don't know, maybe 0.1 nanoseconds to do computation, right? That's almost 1,000x disparity. And we need to buffer a lot of data. We need to cache a lot of data. So this picture that I showed you earlier is there because we didn't care about latency as much. Okay, so I harped on this, but I think I've covered a lot of other things also that are interesting. So that's kind of going to be the nature of these lectures. Hopefully it's going to be interesting, but feel free to chime in also. We're going to cover Amdahl's law. We're going to cover latency later in these lectures. But let me give you the updated version. One of my recent PhD graduates, Minesh Patel, wrote this paper. It's a beautiful paper that talks about the trends in DRAM and also some suggestions for the future. But he did this study where he looked at data sheets from 1970 to 2024. And these are the kind of beautiful data that you can plot if you do the study. So you can see that the capacity has been improving steadily, right? This is capacity per chip. Maybe there's some slowing down over here, but it's hard to tell. I believe there's some slowing down because of technology scaling issues, but people are still pushing. So if you look at 54 years, you get more than 1 million X capacity improvement. Now, my tough question to you is, what is the corresponding latency improvement in those 54 years? Any guesses? I don't expect an exact answer. Anybody brave enough to venture a guess? 2, okay. 5. Any other takers? Pull a number out of the hat. 50, 15? Okay, 15. No, not up. You guys are not optimistic people. What is this? Okay, 1.5, even more pessimistic. Okay, I would have guessed actually somewhere close to probably 1.5 to 2. But it's a bit more than that actually, because in the early times there has been some improvement, but more recently it's been flat. So people were able to improve it a little bit in the early times, but as you look over here, it's been really flat. So people have run out of ways to improve things, which is interesting. Of course, some of this is design choice, right? If you prioritize capacity, as we will see later, your interconnects, if you prioritize capacity, you want to pack many bits, and you want to have those many bits share the same interconnects. This makes your interconnects long, which means that your latency long, right? If you want to actually reduce latency, you want short interconnects. And if you make your interconnects short, you cannot pack many bits on the same interconnect, right? That's the idea. And then there's sensing structures that you need to add. And as you can see, that has not been improved as much, whereas capacity has been improving reasonably well. In fact, some of the latencies are increasing. We're going to get back to that later on. Okay, it's good to do these studies. If you're someone who is really examining the field, I think it's always good to do studies like this that your perspective. Okay, so memory is critical for performance, as we've discussed. Now I'm going to give you some numbers a little bit. Okay, how much time do we have? I don't want to run out of time also. Okay, there's still time. How many people know about dig sites? You know? Okay, that's good. How many other people? Okay. How do you know about dig sites? Say it again? Because of you. Oh, because of me. I see. You watched a version of this lecture before? Okay, so more recent version. Fine. Yeah. So dig sites, that doesn't count as much, sorry. but it's good, you know. It's still prior knowledge. Yeah. But dig sites was the chief architect of alpha processors. Probably not many people know about alpha processors. I'm not going to ask you, but everybody else, probably not. Alpha processors were some of the fastest processors of their times in 1990s and even early 2000s before they lost to Intel, let's say. But they were competitors with Intel. And it's a beautiful ISA. And they designed some of the fastest processors, even faster than Intel at the time. But they couldn't really, let's say, break the x86 barrier, right? Because a lot of software was becoming x86, and they were in a different architecture, alpha. Unfortunately, they couldn't build a software base faster. And then they made some other design decisions that you can ask me about later on that changed things. As a result, they're not around anymore. But basically, after his team designed one of the flagship processors, he wrote this article. It's a one-page article. It's you can see the title over here. It's the memory stupid, right? Playing with the words of some presidential candidate in the United States at the time, saying it's the economy stupid. It's always the economy stupid, I guess. But yeah, but in computing systems, it's the memory. Basically, he said that we designed this beautiful processor. We spent a lot of time, and here's what we wanted to achieve. And this beautiful processor is capable of finishing 4 alpha instructions per clock cycle. And the clock cycle is actually very fast for its time. So it's not easy to do that, let's say, at the time. Unfortunately, on this important workload, it happened to be a database workload that we think we designed the processor for, it's finishing 1 instruction every 4.7 clock cycles. Meaning it's doing what it's supposed to do, meaning completing instructions at 5% or so its peak throughput. Again, take the perspective of a 10-year-old. Is this a good design? If you honestly ask the question to a 10-year-old, they will tell you, what is this terrible thing, right? You designed this thing, it's capable of operating at 100%, and in this important workload, it's doing 5% of its capable of. It's terrible efficiency in that sense, right? Okay, and he basically finishes the article saying that I expect that over the coming decades, memory subsystem design will be the only important design issue for microprocessors. I like his mindset, but I think there's a lot of business and history that did not make this real. I think it's important to. It's becoming more and more real, of course, over time. But I think it's important. It's difficult to change things overnight. Okay, so this is my own PhD thesis. If at some point you write a PhD thesis, hopefully you'll use your thesis in your lectures too. But we worked with Intel. This is my first paper also, actually, from 2003. We worked with Intel to understand where time is spent on the workloads that they're using to design their next generation processors. And we found out essentially the same thing. The excites is suggesting on a larger class of workloads, more than 50% of the time is spent waiting for L2 misses. Okay, I should say that the excites went into it a little bit and said that basically the processor is waiting for data. Most of the time, the processor is waiting for data, so it's not even doing any instruction processing. Right? We found out essentially the same thing. On a state-of-the-art out-of-order execution processor, most of the time the processor is waiting for data. And we proposed some solution to it, which we may cover later in the prefetching lectures. I don't know, lecture 22? One of those. We're going to cover more prefetching also. And we're going to talk about also using machine learning, for example, to guide prefetching. I see Rahul over there. He's done a lot of work in that topic, for example. So this is one way of doing prefetching. Okay, and we're going to talk about that. And we have lectures on that if you cannot wait. And this is implemented in some processors. Okay, but more recently, this is a beautiful paper by Google. We'll probably also assign it as one of the homework assignments or part of the homework assignment, where they analyzed, according to them, all of their data center workloads, and they found out essentially the same thing. This is, according to them, all of their data center workloads at the time, again, a state-of-the-art general purpose Intel processor. And most of the time, as you can see, the processor is bound by backend, and most of these are waiting for data to come back from memory. Yeah, as you can see over here, the processor is finishing instructions less than 20% of the time. Again, what it's supposed to do, right? The job of a processor is to process instructions and complete them. Some of this is wasted on mispredicted branches, for example. Some of this is wasted on cycles where you cannot do anything. You cannot complete instructions because you're waiting for data, right? And that number is huge, as you can see over here. So this front-end bound is because maybe you have some bubbles in the pipeline because you had a branch misprediction, for example, or some other misprediction, some other stall in the front end. Okay. Okay, so hopefully it's clear. So now I put some data to the memory bottleneck. It doesn't look very good. And in some workloads, as we will see, this number is not like, not even 50%, not 50%. No, it's more like 90%, 99%, 99.9%. Most of the time, you're waiting for memory, basically. Okay. So we're going to look at memory in a modern system, but this is an old AMD Barcelona processor. You can see that at the time, cores were pretty big. Over time, memory systems grew and grew. I'll show you the more recent AMD processor in a little bit. But you can see that memory still occupied a lot, even early 2000s over here. There's a memory controller, DRAM interface. There's a shared cache over here. There are private caches at the time over here. Okay, this may be shared also, I don't remember. And then there's other memory control, interconnect and cores. But if you look at cores, a lot of it is also memory, as you can see, right? There's a lot of L1 caches and register files. Okay, just to give you a historical perspective, memory L2 caches were not on chip in the past. So because of the success of Moore's law and technology scaling, we're able to put more and more transistors. And over time, the processor chip started consuming a lot of other stuff that belonged to the system, right? L2 caches was one of the first to be consumed, right? Over time, memory controller got consumed. Over time, other communication interfaces got consumed, like PCIe, etc. I think over time, we're going to consume more, assuming this continues. But I don't know how far it will continue with the cost and reliability requirements and power requirements, right? So people are looking at 3D stacking also. Once you start doing 3D stacking, you may actually put more, but you're limited by thermals once if you're actually doing 3D stacking, because how do you cool these layers in the middle, for example? Or even if you had 2 layers, how do you cool both of those layers? Okay, so this is how L2 cache got consumed. And this is a more recent processor, which has a lot of memory over here, as you can see. This is the more recent AMD processor I promised. As you can see, most of it is cache, that green part. And this is not all the caches. There's L1 caches that I don't circle over here. And you can see other things that are consumed over here. System management unit. What is that, right? A lot of power management, etc. There's debug, wafer test bumps, etc. And then global memory interconnect, more fabric, essentially, more interconnect. Okay. So that we don't pick on only AMD, there's IBM that does the same thing. You can see other interconnects over here. So outside of the chip is really dedicated to a lot of both mixed signal processing to do interconnects, as you can see. So most of your chip is really memory and communication. Internally, most of the chip is memory and communication also. And even the sides over here, memory and communication. Okay, this is more of a GPU. Again, the same thing. And today, actually, people are experimenting with very interesting technologies like 3D stacking. You can actually take a processor chip and on top of that stack with using different technologies like hybrid bonding, for example, memory chips. And AMD is putting cache chips on top of a processor chip. So this is very interesting technology. It's good to enable it. Are we using it in the right way in the system level? It's a good question to ask. Right? Does it really make sense to keep adding more and more caches? It's really interesting. Yeah, it's the easy thing to do, but does it really make sense? Okay, and then there's other systems where, so the way I think of the processor chip today is we have a lot of SRAM over here, and then we have a lot of DRAM, and then we have a lot of darkness, which is the storage. And a lot of people forget about the storage, but in this course, we're not going to forget about storage because it's really important. Especially when data set sizes are growing, this darkness becomes even more important, right? And I'm going to give you the energy perspective a little bit, and these numbers will be a bit crazy, as you will see. But storage system over here has actually processors inside it. It's a system by itself, which is really interesting. So we have the system, and inside that system, we have the storage system, which can actually do processing internally. But people don't use it for processing. Okay. So this is another machine learning accelerator. I picked on this one from Sambanova. But they actually are trying to do machine learning acceleration in a different way. They're not relying on huge amounts of SRAM, but they're actually relying on multiple levels of memory, as you can see over here. So they have high bandwidth memory, they have high capacity, I think LPDDR, and they have a lot of SRAM still, but not a lot. 512 megabytes is nothing today. Remember the 44 gigabytes of Cerebras with Wafer-scale. This is not Wafer-scale. This is much smaller. So even in a machine learning accelerator chip, a lot of it is memory, as you can see, right? They don't have a nice die picture that I can pick on. Okay, so this basically concludes my point. In the end, memory system is really most of the platform, but it's really the bottleneck of the system still. Okay, now let's talk about energy. Any questions on performance? I didn't cover everything in performance because there's the quality of service aspect of it, but we will talk about that a little bit later. Let me talk about energy, because this is something that most people don't talk about in general. Like when you take a computer architecture course, have you covered energy? How many people covered energy, I guess? Okay, you have, that's good. How many people did not cover energy at all? Okay, more hands, that's good. That was my expectation. That's good that you covered energy. You took it from Sogata? Well, there you go, okay. Depends on who you take it from, I guess. You should always qualify the question, maybe. Okay. Okay, basically, this is even worse. And it's even worse because of what I will show you next. But if you look at this, as early as 2000, there's a beautiful paper from IBM, from Charles Lafergie, where they studied these huge systems that IBM used to design. They still designed, actually. These are called big iron systems, essentially. And they found out that more than 40% of the energy is spent on the off-chip memory hierarchy, which is a large number. And there are other studies by both IBM and NVIDIA where they show that more than 40% of the system power is spent in DRAM. That's a lot. This is without HBM, even without HBM. More recently with HBM, the number is actually much higher because HBM, high bandwidth memory, is much more power hungry than DDR memory. And one of the issues that we will discuss in this course that also affects the technology scaling aspect is a technology like DRAM consumes power even when it's not used. It's not only a volatile technology, it's also something that needs to be periodically refreshed because of cell leakage. You store data in the cell in terms of charge, and over time that charge leaks. Those electrons leak out of the capacitor. And as a result, you need to refresh it periodically. So my cell phone, for example, right now is refreshing its DRAM. It's trying to be very efficient in how it does it, but it's still refreshing itself. Okay, we're going to talk about that. That's a fascinating problem, I think. Some other memory technologies don't have it as bad, and we're going to talk about that also. Okay, let me give you some numbers in terms of how bad energy is. We should really update these numbers based on the digital design and computer architecture course. We have better numbers than what's depicted here, but I'm going to use these numbers. These are relatively old numbers. Numbers may have changed. In fact, they have changed depending on the technology, but the discrepancy remains similar. So this is showing, these are numbers from NVIDIA, chief scientist of NVIDIA, Bill Daly. Essentially, in this slide shows that a complicated arithmetic operation, a 64-bit double precision floating point operation consumes 20 picojoules with some technology assumptions. Whereas a DRAM read or write consumes 16 nanojoules. So that's 800x difference. Okay, you can say, okay, this is too much. I'm going to optimize it, and people have optimized it, and the number is closer to 100x, maybe 200x, between 100 and 200x. So basically, a memory access today consumes 100 to 1000x the energy of a complex addition, 2 orders of magnitude at least. And this has actually been the success of technology scaling. The technology scaling enabled us, logic scaling enabled us to reduce the size of the transistor, make it faster, make it more energy efficient until some time ago. But over the course of the scaling, interconnect and memory technology or capacitor did not scale, essentially. What happened? Well, not in the same way, at least. Right? As a result, interconnect and memory became a much bigger bottleneck over time. So these numbers, if you look at these numbers 60, 70 years ago, they're not as bad. But today, they're pretty bad. So this is, of course, good to ask the question. If you want to add two numbers and write the result back to memory today, and you don't have any locality, meaning you're not going to reuse any of those numbers, again, in your computation, does it really make sense to bring those numbers to the processor chip all the way from main memory? You're wasting 3 times 800x energy in these, according to these numbers, to do a very simple computation. Of course, it's an optimization problem. It's always good to ask the question, when should I bring the data to the processor chip? When does it make sense to at least break even in terms of the energy consumption compared to doing the operation on the memory side, for example? It's good to think about these things. But today, we're bringing everything to the processor because we have no other option. Bring everything to the processor, do the operation, and then write them back whenever you're done. Okay, just to give you an idea, if the operation is simpler, this is for a 32-bit integer operation as opposed to 64-bit floating point, the discrepancy between memory access and the operation is much higher. That's 6400x, assuming those numbers, of course. That's a lot. And this is not even taking into account storage. So usually what you do is you bring the data from storage to memory and then memory to caches and then caches to the processor. If you actually take into account storage, add at least an order of magnitude over there. So this is what I call the numbers as being crazy. To do one very simple arithmetic operation, we're wasting, okay, I'm going to reach a little bit over here and say you're wasting at least 64,000 times the energy of that operation. Does it really make sense? Or when does it make sense to do so? It's good to ask this question. And as I said, today people are trying to do even lower precision operations, 32 bits, reduce it to 4 bits, reduce it to 2 bits. That cuts the cost of energy of the operation a lot. That cuts the cost of data moment a lot also, but not a single access usually. Usually you aggregate over accesses. So with simpler operations, this number actually becomes even worse, I think. Okay, so we've done a lot of studies to understand the effect of this data moment on overall energy consumption of the system. We've written some papers. We're going to talk about some of these papers later on when we discuss processing near memory. This is a study that we did with Google. I spent part of my sabbatical at Google, and one of my students did some internship over there also. And we found out essentially more than 60% of the total system energy spent on data moment on mobile workloads, which is a lot. And these are average use cases. We were not really trying to let's say, use the most data intensive cases. And more recently, we repeated the study with the edge machine learning accelerator that Google had at the time on machine learning models that they had at the time. And we found out that the situation is even worse over there. Basically, more than 90% of the total system energy is spent on memory in those large models. Just to give you an idea, this is a breakdown from that paper. We studied a bunch of Google proprietary models that is executing on the edge machine learning accelerator. This is designed for Google phone, for example, right? If you have a Google Pixel phone, it probably has this sort of machine learning accelerator, maybe an improved version, depending on how old your phone is. Essentially, if you look at these machine learning models, this is machine learning inference, LSTMs and transducers, which tend to be much bigger models compared to CNNs, convolutional neural networks, and RCNNs. And we find out that most of the system energy is really spent on off-chip interconnect and DRAM, because they're really moving the parameters in and out and in and out and in and out from the accelerator all the time because it's huge. The machine learning models are huge. Okay, we're going to get back to this also. We're going to discuss this. But basically, if you design the system in a better way, enable computation capability on the memory side, and do some of that inference on the memory side, in a similar accelerator that's designed near memory, you can reduce the energy by about 3x, as you can see over here. You're still bottlenecked by DRAM, as you can see, because you're still accessing memory over there. But that bottleneck is much smaller at that point because you're much closer. Okay, so basically, I think one trend, all of these, both performance and energy trends, point to the need that we do not want to move data. That's the title of the slide over here. So I believe, and we're going to talk about this a lot in the next few lectures. How do we enable a paradigm shift where we can enable computation with minimal data movement, as opposed to limiting ourselves to doing computation only in a small fraction of the processor chip? Can we really compute where it makes sense, where data resides? And this could be anywhere, right? In the sensor also, when you have data captured in a sensor, assuming that's the source of the data, then you do the processing, or at least some of the processing on the sensor side. Right? So these are more data-centric architectures. So just to enable your imagination a little bit, we're doing computation only in a small fraction of this SRAM-dominated chip today. Why not actually enable computation everywhere over here, and then figure out how to take advantage of all of those computation resources that are more tightly coupled with the data? Sometimes it makes sense to bring the data over here, but many times it doesn't make sense to bring the data, even from the sensors, perhaps. So this is a very nice area, I think, which we're going to talk a lot about. I think I'm going to stop here, probably. Tomorrow, I'm going to pick up over here, and we're going to talk about some other issues, and then we're going to talk about start talking about processing in memory and processing near memory. But before we part, any burning questions? No. Okay. Hopefully, I'll see you all tomorrow.